Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. First, we would like to thank the ICBB 2020 committee for letting us to present our paper we entitled The Density Functional Theory Study of Astaxanthin-Metal Complex to Native and Glycated Human Serum Albumin. And our team member consists of me, Syahputra, and there is Dr. Sriwidyarti, Dr. Ahmad Sabaruddin, Professor Dr. Djoko Wahono Sutmaji, and the last is Professor Sutiman Bambang Sumitro. Okay, let's jump into the introduction. Well, as we know, diabetes mellitus is a degenerative disease that tends to experience a complication due to the change of physicochemical of blood. And this main characteristic of changes in physicochemical of blood is a change in the red blood viscosity, which is very related to the functional aspect of albumin as a transporter and a scavenger. And in this diabetes mellitus case, is likely to increase free radicals. And free radicals are normal component in our cellular metabolism, but if the amount of excess free radicals are more than normal, it can cause cell damage that impacts oxidative as well as molecular and is a major factor causes the emergence of pathological condition. And this oxidative damage causes a conformational change of the protein that is often found in cases of diabetes and a variety of degenerative disease. Albumin in type 2 diabetes mellitus or T2DM undergoes conformational changes that affect the ability as an endogenous scavenger. And one of the causes of damage to this protein, albumin, is if albumin itself exposed to AGE or advanced glycation end product. And the process of glycation itself can aggravate the condition of diabetes mellitus where glycation agents such as galactose, ribose, and glyceraldehyde accelerates the glycation process and also have detergent effect on albumin which are unfolding and the opening of hydrophobic surface. Also amyloid formation on the structure of human serum albumin or HSA. And then the modification site albumin that has occurred on glycated albumin including Q199, Q281, and etc. Treatment of diabetes mellitus type 2 patient is generally given with metformin, and metformin itself can lower glucose level in the blood. And as we know, metformin is the first line of treatment for T2DM patient, and this drug has the ability to be used in conjunction with other diabetes drug due to efficacy and safety. But like any other drug, metformin has side effects such as vomiting and nausea. Even the most case is lactic acidosis state, especially in T2DM patient with kidney and liver dysfunction. This research using a new perspective based on physicochemical properties of glycated albumin, and one of the therapeutic agents into a compelling study in this research is astaxanthin. Our previous studies showed that astaxanthin can be used as a therapeutic agent for preventing conformational changes on glycated albumin. We already published the result in a Scopus journal before with astaxanthin as a single compound, and in this study, we tried to complexing astaxanthin with one of essential metal ions. Astaxanthin, the inorganic complex with metal cations, were known to produce chelating metal ions as antioxidant due to the useful properties of metal cations in donors and electron acceptors, referred to as Lewis acid base. Metal ions play an essential role in many biological processes due to the specific role that only those metals have. It can improve the ability of astaxanthin as a radical scavenger of free radicals. And metal ions that can be coordinate with astaxanthin are Cu2 plus or cuprum. Cuprum is one of essential metals required in various catalytic processes. Cu in the form of metal ions or Cu2 plus can form coordination bonds with oxygen atomic donors, and that's why we choose to use Cu2 plus in this experiment. And for that, we are using the FT and molecular dynamic simulation to know the result of this astaxanthin complex with metal ions itself. The DFT itself is the electron density of any system determines all ground state properties of the system. In this case, the total ground state energy of many electron system is a function of the density. Meanwhile, the molecular dynamic can help to understand the stabilization of protein molecule in a specific environment, and that's why the objective of this research are to characterize antiradical property of AXX or astaxanthin ASX plus Cu2 plus in the form in one metal ions or astaxanthin plus Cu2 plus and astaxanthin plus 2 Cu2 plus or in the form in two metal ions with density functional theory or DFT and to compare the capability to prevent conformational changes on glycated albumin. And for methods we were using is first in data mining, and after that we are going to use in Avogadro and also Gaussian ICBB2020 and Gauss View 06.0, and also docking with Pyrex Primal DS Studio 2016, and also it ended with Iazara. And also for data mining, we got it from two resources. At first is PubChem, and the second is PDB or Protein Data Bank. And from Protein Data Bank, we got albumin, or we call it as human serum albumin, with the ID of 4K2C. And in PubChem, we got astaxanthin, copper ions or Cu2 plus, glucose, and metformin. And also, we got the isomeric smiles for the next step. And for the Avogadro itself, we built the complex, and there are two complex that we built in Avogadro. There is Astax with one metal ions, and second is Astax with two metal ions. And also after that, we are going to set up the force field UFF with number of steps is 500, and also we use the algorithm or stepus descent, and also we optimize the geometry so that our complex can be used into the next step. And in this study, two different metal cations such as CO2 plus and 2CO2 plus and astaxanthin were considered, and density functional theory as implemented in Gaussian O9 was used for all calculation. In job type, we were choosing op plus free for optimization and frequency with ground state and DFT with global hybrid 3 parameters B3, LYP density functional, and the LAN L2DZ basis set. We choose this basis set because it works wonderful with organometallic compound. We were able to verify optimize minima using harmonic frequency analysis. As previously reported, the density functional approximation calculation using LAN L2DZ pseudo-potential are adequate for metal interaction. For example, those of zinc, cadmium, and mercury, and this also includes scalar relativistic effects. And also, the absorption spectra of astaxanthin-metal cationic complexes have been computed with time-dependent density functional theory or TDDFT using the same functional and basis set. For solvation, we were using a polarizable continuum model, specifically with the integral equation formalism or EAF-TCM with ethanol as solvent in order to make a comparison with a real-life experiment. And after that, we are using docking with Pyrex, Pymol, and Discovery Studio 2016. And in this slide, you can see the FINA search space. And also after that, we are going to molecular dynamic simulation using IASARA with MD-Run, MD-Analyze, and MD-Analyzers. And we are going to result in discussion, and we divide into three sections. The first is optimized structure, vibration, ER spectra, HOMO, and LUMO. And as we know, HOMO is the highest occupied molecular orbital. Basically, HOMO is where the electrons are donated and most available for bonding and most weakly held electrons. And the LUMO itself is the lowest unoccupied molecular orbital, where LUMO is received electrons, lowest energy orbital available, and characteristic for electrophilic component. And the second part is the electronic energy or thermal, heat capacity, entropy, dipole moment, polarizability, and the last section is the binding affinity, potential energy, binding energy, and movie visualization. So here is the result of astaxanthin in initial state. We can see the optimized structure that we got from Avogadro. There is only one kind of structure here that have been optimized. And in vibration, we can see there are two modes of vibrating in beta-ion rings. And in AR spectra, we can see the lower absorbance value in AR spectrum in fingerprint area. And what is the fingerprint area? Well, fingerprint area is an area of spectra that confirm the metal ions can bound into the astaxanthin itself. So here, because astaxanthin in initial state, there are no absorbance here, still in the lowest part of value in ER spectra. And after that, we got the HOMO and LUMO pattern of astaxanthin in initial state. We can see that in astaxanthin in initial state, positive charge and negative charge of HOMO and LUMO. So it only happen in backbone area. And after that, we are compare it to astaxanthin with Cu2 plus in one metal ions. Here, the metal ions of Cu, the optimized structure become more different, and the vibration itself is different than the previous one. The vibration happen in all of this astaxanthin body, and in ER spectra, we can see the more higher absorbance value confirm that CO2 plus is already bound into astaxanthin, and the Homo and Lumo show that the pattern, the astaxanthin is far more better in receiving and donoring the electron. And it's also happened in astaxanthin with two metal ions here, two metal ions, and if optimized structure, it's also similar with the previous one. And in vibration, all of this become more vibrating, and AR spectra is far more higher absorbance value compared to the other one. And Homo and Lumo show the different state of astaxanthin for receiving and donoring electron. And here is the result of the FT theory from Avogadro and Gaussian O9W. We can see that in electronic energy, astaxanthin initial state is have less value in compared to astaxanthin with metal ions. It showed that astaxanthin with metal ions complex to them is far more better in electron management, and compare it to entropy, the equilibrium itself is far more easily to reach in astaxanthin with metal ions compared to astaxanthin in initial state. In head capacity itself, astaxanthin to CO2 plus and astaxanthin CO2 plus is far more highly to have this head capacity than astaxanthin in a normal state. And after this, we can show that the binding site and interaction type, and we can see in the table the protein itself has glycated human serum albumin complex with ligand such as astaxanthin, metformin, and astaxanthin with metal ions show that the binding affinity from astaxanthin have minus 8.9 compared to with metformin is minus 5.0. What does that mean? The more negative binding affinity means the ligand it's more easily to bound into the protein. And in astaxanthin with metal ions is far more negative than the previous without the metal ions. And in this interaction type, we can see that in GSA and GHSA with CU2 plus in two different form, such as CU2 plus and 2CU2 plus have the same pattern, which is hydrogen bond, p-alkyl bond, and also alkyl bond. And compared to GHSA and astaxanthin normal, it means it only have two different type of interaction type, which is alkyl bond and also hydrogen bond. And here in molecular dynamics, we can show that potential energy and binding energy already achieved the equilibrium, means our data is valid and can be used to analyze the RMSD backbone. What is RMSD? RMSD is root mean square deviance. When the root mean square deviance is the value is more than 3 nanometers, it means the protein become more unstable, and it can show you that in the pink one is the glycated human serum albumin, which is far will going up there, and it become more unstable if we are adding more longer into the simulation data. And in glycated human serum astaxanthin in blue is more less than the previous one without adding astaxanthin. And when we are adding the metal ions, it will show more less than the blue one. It means astaxanthin with metal ions is really capable to prevent unfolding events, and it can prove with this movie visualization data. We can see that in A is the human serum albumin in the end of the simulation is still intact, and between the site A and site B, and glycated human serum albumin already have this unfolding event here from the site A and site B. And when we are adding astaxanthin, it will close the gap and prevent them from unfolding event. Same with the astaxanthin with metal ions. So, but these two have a more similar pattern to the normal one, or the normal patient without type 2 diabetes mellitus. So we can conclude that by adding metal ions into the astaxanthin and complexing it with the glycated human serum albumin, it will increase the ability of astaxanthin to prevent glycated human serum albumin from protein unfolding and make it to perform its normal function. Thank you. Have a nice day. Wassalamualaikum warahmatullahi wabarakatuh.